little reminder on what we covered last week, since it was last week. We ended with this problem. So there's like 10 screens on my window. Okay, now I got it how I want it. Here's what we went over. You guys remember this slide right here, units of concentration. We talked a lot about, okay, we defined what a solution is. Solution has two parts, solvent and solute. Solvent is what is dissolving the solute, what is being dissolved. And then we talked about guidelines for solubility, how to predict or know when two things will be soluble or miscible if they're two liquids. Like dissolves like, okay, polar with nonpolar, or sorry, polar and polar solute solvents will dissolve, nonpolar and nonpolar. But polar and nonpolar things don't mix. And then we talked about temperature and how we can use temperature to manipulate solubility. Okay, so somebody remind me, when you have a solid dissolved in a liquid, a solid dissolved in liquid, does the solubility increase as you heat it up, or does it decrease? If you have a solid dissolved in a liquid, does the solubility of that increase as you heat it up or decrease as you heat it up, as you add heat? Remember the graphs we looked at? Right here, a solid dissolved in a liquid. As you increase temperature, the solubility increases. All right, for gases, it was the opposite. As you increase temperature, the solubility of gases in a liquid decreases, okay? Remember those trends. And then we talked about Henry's Law. There is a problem on Henry's Law. I actually have an email from a student about this. I've got to respond to it today. There's a problem on your homework about Henry's Law, and it's like gases, parts per million type of thing, ppm. And it's a challenging problem on the homework, okay? So spend some time looking at it, but reach out to me if you need help. It's all to do with Henry's Law. Concentration of one condition divided by pressure equals concentration of another condition divided by that pressure. And then we worked a problem on it. Okay, remember units for that concentration are gram per 100 ml, and you do not divide by the 100. Then we talked about units of concentration, weight, volume, percent, and molarity, and this is where we left off. We started working problems on that. So we worked all these problems right here, and now we're going to solve one. I'm going to skip this problem at the bottom. We're going to solve one on molarity, okay, just as a quick review before we move on to any new content. So remember, molarity is abbreviated with a capital M, moles of solute divided by liters of solution. And here's the problem. If you dissolve 2.335 grams of H2SO4, that is sulfuric acid, and dilute it to 50 mLs, what's the molarity? Okay, what's the molarity? So we have grams of our solute. Water is the solvent. We need moles though. So we've got to get a molar mass to convert grams to moles. Okay, so remember how to calculate a molar mass? We've got hydrogen, sulfur, and oxygen. So for hydrogen, we've got two of them. And you look at a periodic table and you grab the number, the mass number on the periodic table. It should be 1.01 for hydrogen. Well, yeah. And then we'll add that up. For sulfur, can somebody actually tell me what it is for sulfur? I don't have that. Is it around 16? Or more than that, probably. It's probably way more than that. Oxygen is 16, so it should be like 32. Yeah. Okay, so we've got sulfur 1 times 30. Whoops, that's a 2. 32. And then oxygen, we've got 4 of them. So we'll just add all of that up. Don't you guys get 98? Okay, so now we're going to convert to moles. We've got 2.335 grams of H2SO4. And I know for every 98.02 grams, that's 1 mole. So that equals how many moles? 2.335 divided by 98.02. Molly got 0.0238 moles. What y'all got? Okay. So now what we're going to do is we've got moles, and that, looking at our equation, we're going to plug that in right here. So we're trying to solve for molarity. So we're going to plug moles in on top, liters of solution on bottom. Well, we've got milliliters. That's our volume. So we need to convert that to liters. So 50 milliliters times, there's 1,000 milliliters for every 1 liter. So we're just taking the volume, converting milliliters to liters. You should get 0.05 liters. And then we plug that in on the bottom. So what you should ultimately do, molarity, I'm just going to abbreviate with a capital M, is going to equal, in this case, 0.0238 moles of H2SO4 divided by 0.05 liters of the solution. Remember, this is the solute on top, and this is solution on the bottom, which is solute and solvent. So what do we get for the total molarity? Kylie says 0.476 molar. Or you could write 0.476 moles per liter, right? That's what molarity is, moles per liter. Okay, questions on this problem? So on the exam, the next exam, you should definitely be able to calculate for me. It could be a multiple choice question. It could be a file response, a weight volume percent. If I give you grams and, milliliters of your solution, you should be able to calculate weight volume percent. Or if I give you the percent and I ask you for how many grams, okay? We worked a problem like that last week. Or you should be able to calculate molarity, okay? Or what if I give you the molarity? Like, what if I were to give you this part and say how many moles of solute? Okay, I would give you 2 of the 3 pieces of the equation. You solve for the third. All right. But I want to go back to this right here, expressing these units like this. Molarity is a relationship between moles and liters, just the same way that molar mass is a relationship between grams and moles. Okay, it's relating 2 different units. And because of that, what we can always do with conversion or with units like this is we can use them as a conversion factor. So you guys remember the 3-part problems we did back in chapter 6? It's a fancy word, is stoichiometry, doing problems relating mass and moles, but with a chemical reaction. Well, we're going to learn how to use molarity as a conversion factor. This is going to be a simplified problem, and then you can ultimately do the 3-part problems with molarity instead of molar mass. All right, let's read this problem right here. This is how I'm going to demonstrate how we would use molarity to convert between moles and volume. A blood alcohol content of 0.065 molar is how you would say that, is enough to induce a coma. So this is technically 0.06, you could say moles per liter. Okay, that's what molar is, moles per liter. If the total blood volume of an adult male is 5.6 liters, how many grams of alcohol are necessary to reach this concentration? So we're given the volume and we want to know how many grams of alcohol. All right. So this seems a little confusing because molarity doesn't relate liters to grams. Okay. We're given liters and it's asking for grams. We don't have anything to directly go from liters to grams, but we can go from liters to moles with molarity. And then easily we can go from moles to grams. All right. So what we're going to do, this is showing you this little diagram down here. We're going to start with the volume of the blood, 5.6 liters. We're going to then, step 1 is use molarity to convert from liters, okay, that's the volume, liters, to moles, all right? And it says ETOH, this is alcohol, this is ethanol, which is in alcohol, okay? Anytime you have an alcohol bottle, you can see the ethanol content. And then we're going to use the molar mass to convert to grams, which is just the unit for mass. All right. So let's start with 5.6 liters. That's the amount, the volume of blood in an average adult male. And now what is our molarity? It says use molarity to convert from liters to moles. So we said it's this right here, 0.65, and I write out moles per liter. That helps me see where, if I need to put liters on bottom or on top, I want liters to cancel. So I'm going to write that conversion factor just as is, the 0.065 moles on top per 1 liter on bottom. That is the molarity. okay? And the problem is written just with the capital M, but it's moles per liter. That's what capital M stands for. All right, then the last thing we're going to do is convert to grams. So we need to know for every 1 mole of ethanol, how many grams is it? Okay, so we've got 2 carbons, 6 hydrogens, and an oxygen. We know carbon is the 12.011. We know hydrogen, there are 6 of them, times 1.01. Oxygen, 1 times 16. When you add all that up, you should get 24 plus 6 is 30. And 16, you should get 46.021. Is that what you guys get? Am I off? Is it 2-2 or 3-2? I think I'm off on the decimals. What'd y'all get? I think it should be 3-2. Anybody double check me? .082. Okay, thanks. I knew I was wrong. Gram per mole. All right. So now we're just going to plug that in. So you do 5.6 times 0.065 times 46.082. How many grams of alcohol would it take to put an adult male into a coma? What a terrible problem. That's depressing. 17.5 grams, okay, of just straight alcohol, obviously, or just straight ethanol. Obviously, alcohol that you buy at the store is not straight ethanol. Okay, so take a lot more of any sort of alcohol, but that amount of ethanol across, whatever type of alcohol it contained in would be the answer there. So, okay, questions on how to use molarity to convert between here. What we did is we converted from liters to moles using the molarity. Okay, if you're comfortable with that idea, now I'm going to introduce what I call the 3-part problem with molarity. Again, you've already seen this format back in chapter 6. We're using molarity, and just stoichiometry is the fancy word for converting between mass and volume or mass and moles. So if we have some sort of balanced equation, a balanced chemical reaction, A plus B makes C and D. And you are given the volume of, so now we're dealing with solutions. Chapter 9 is all about solutions. So if you are given a volume, like you have 200 milliliters, or you have 0.5 liters of solution A, okay, for reactant A, and you want to know what volume of solution B do I need to react with solution A to make my products. All right, so any problem could say this. You've got I'm just making up numbers here, 0.5 liters of solution A, and it could say how many liters or milliliters of solution B. Okay, so that could be kind of the format of the problem. So the way you would answer a question like that or a problem like that, which is a very valid thing, all kinds of industries who make solutions and make products that are liquid, they have to do stuff like this all the time. You take the volume of solution A, you would then step 1. Here's the 3-part. Here's where the 3-part steps come in. Use molarity, just like we just did in that blood alcohol problem, and convert from volume to moles of substance A, okay? Because molarity is a mole per liter. And you're starting with a volume, which is either milliliters or liters. So we're going to convert from liters to moles. And I want to make a point. If you start out with liters, then you have no initial conversion you have to do, but if you're given, a certain number of milliliters, you always have to convert that to liters first. All right, then you can use the molarity as a conversion factor. Once you have moles of A, you guys have done this all day long. Use coefficients in the balance equation to find the mole ratio. You guys remember how to find a mole ratio? Just look at your balance equation. It's got to be balanced. Get the coefficients. We're going to practice doing this in just a second. That will convert you from moles of A to moles of B. So that was step 2, the mole ratio. Step 3 is we're going to then use the molarity of substance B. So up here we were using the molarity of substance A. Now we're going to be using the molarity of substance B to convert from moles to the volume of solution B. Okay, this is again a moles to liter type of conversion. All right, so let's look at a real example, because sometimes these things are hard to comprehend just looking at diagrams like this. So let's actually put all these 3 steps into play in this order. I'm going to skip over this problem because this one actually, it does milligrams, and that's not the one I want to do. I'm gonna go to this problem right here. This one is going to walk us through those steps exactly. The slide above is a good practice problem, but it's a little bit off topic for what I want to cover. So calcium carbonate reacts with hydrogen chloride, hydrochloric acid, to make calcium chloride. So this would be like if you took an antacid pill in your stomach, this type of reaction could happen. Antacid contains things like calcium carbonate. Your stomach contains things like hydrochloric acid. It makes calcium chloride, water, and carbon dioxide. How many milliliters? Okay, so this is where the question begins. So we're gonna call whatever it's talking about. This is how many milliliters of calcium carbonate. So this is gonna be what we're looking for. Okay, we're looking for that. So, it's how many milliliters of a 0.22 molar, and again, you could write this as 0.22 moles per liter. Okay, that'll help you see the units to convert between. How many milliliters of a 0.22 molar solution of calcium carbonate are needed to react completely with 25 milliliters of a 0.5 molar, which is 0.5 moles per liter, solution of hydrochloric acid. All right, so for hydrochloric acid, HCl, you are given the volume and you are given the molarity. So that is where we're going to start. You can call this substance A, you could call this substance B. Since we're given both things for substance A, we're looking for something on substance B. So we need to start with a balanced chemical reaction. Okay, otherwise we don't have a mole ratio, because we're going to need a mole ratio. So calcium carbonate, anybody tell me the formula for calcium carbonate? Carbonate is a polyatomic. Calcium, thank you, Kristen. Ca, which is a +2 cation, CO3, which is a -2 polyatomic, so just one each. Reacts with HCl, and it gives a lot of products. It gives calcium chloride, CaCl2. You guys all know what water is. Whoops. And carbon dioxide. Okay, so here's our equation, but it's not balanced just yet. Goodness, that's a big eraser. To rewrite. Okay, so now we got to balance it. So where do I need to put coefficients to get this balanced? Two on HCl, Maria says. I like that. Is it balanced after that? We got one calcium, one carbon, 3 oxygens, 2 hydrogens, and okay, I think we're done. Fairly easy. So we can obviously tell our equation here is asking us about calcium carbonate and HCl. These are the 2 things that are important in our problem. So we're going to need the mole ratio between these 2 items. And so we are going to start, remember, I'm going to scroll back up to the diagram for just a second. Be right back. We're going to start with the volume of HCl. So let's go to our problem and find the volume of HCl. That is right here, 25 milliliters. but I have to convert that to liters first. Okay. So I'm gonna zoom in right down here. 25 milliliters. That's going to give me 0.025 liters. All right, now I can begin my problem. Now this is a 3-step problem. So somebody tell me what I need to do first. What did that diagram say? The first thing, what should I do? Looking at that diagram, convert with molarity, okay? And which molarity? It is this one right here, the 0.5 molar, 0.5 moles per liter. I want liters to cancel and I want to convert to moles. So for every 1 liter, it's 0.5 moles. And we're talking about HCl here. I like to label, again, what compound. Particularly here because that will help me plug in my mole ratio correctly. So that was step 1. Okay, we used molarity of substance A and we converted, which is HCl in this case, from a volume to moles using molarity. This is going to be now step number 2. What is step number 2? Plug in the mole ratio. So what is our mole ratio here? I need moles of HCl on bottom because I want that to cancel. I want to convert to moles of CaCO3. 1 to 2. Yep. So put 2 moles HCl on bottom, 1 mole. And I'm just, again, I'm looking at the coefficients in my balanced chemical reaction. So far, liters cancel, moles of HCl cancel. And then step number 3 is what? 3-part problem. What should we do next? What are we looking for? Remember, the question says how many milliliters. So we're looking for a volume of calcium carbonate. We have moles of calcium carbonate right now. How do you go from moles to volume, which is liters, moles to liters? You've got to use, there you go, molarity. And that's the 0.22 this time, the one given right here. And I want moles to cancel, convert to liters. That's what Kylie said, liters on top. So it's for every 1 liter, it's 0.22 moles of CaCO3. And moles will cancel, and then we'll have a volume. All right, so what do we get? You've got to do, start here, 0.025 liters times 0.5 divided by 2 divided by 0.22. .025 times 0.5 divided by 2 divided by 0.22. Anybody got it? 0.028. And what are the units here? Everything cancels except liters. Okay, but the question says how many milliliters. So we got one little step in the end. We're just going to convert back to milliliters. All right, because that's a pretty small number of liters. It'll make more sense if we read it in milliliters. So that's just 28 milliliters. Okay, so if I've got 25 milliliters of 0.5 molar HCl and I react it with 28 milliliters of my calcium carbonate, I'll make all products. I'll use up all my reactants. And those are the equal volumes for those amounts based on the mole ratio and the balanced chemical reaction to give you your products. Okay, there we go. So you see how that's a 3-part problem? Plug in a molarity for substance A, then a mole ratio, and then a molarity for substance B. Okay. Any questions on this style problem? This could definitely be a file response question on the exam. That was like a 5-part problem, yeah. Because why? We had the initial conversion to liters and then the final conversion back to milliliters. So that was 2 more steps. I agree. But the core of it is this part right here, those 3 steps.
Could you scroll up real fast to the where it shows the step by step?
If anybody wants to take a screenshot or something.
Thank you.
You bet. Like I said, this problem is similar. The only thing is that you're starting with milligrams instead of milliliters, so it kind of throws people off. But attempt this one if you want, now that you kind of know. But it's just you're going to be using a molar mass first versus a molarity. It's kind of weird, but all right, that's it for how we use molarity as a conversion factor. I know that's only one problem that we worked on that, so I'll definitely be doing more on a review before exam 4 because I think those problems are pretty hard. But we've got several other topics to hit today. So I'm gonna show you dilution problems. And so when it comes to solutions, another part of working with any kind of solution in a hospital or a clinic, especially in hospitals, a lot of times when you order things from companies, let's say you need a solution of iodine. Why is iodine useful? Anybody work in a hospital use iodine? What does it do? Helps like cleanse things, right? Use it as a cleaner and cleanser. And so you might get a really concentrated solution and you don't need it that concentrated. Okay, so often you're given a solution that's more concentrated than you need. We call this a stock solution. And we must add more solvent to dilute the solution to the concentration that we actually need. Okay, so the concentration we actually need is called a working concentration. Okay, especially if they order like IV bags and stuff. I don't necessarily know what concentrations, but sometimes those things have to be diluted as well. All right, so how do I know how much solvent to add to get the concentration I need? That's kind of the question here. How do we go about diluting this? Well, there's an equation for dilutions, and it's this right here. So again, there's lots of equations for exam 4. You've already got weight, volume, percent. You've got molarity. You've got the whole 3-part process. Now we've got a dilution equation. So I would maybe get like a little index card and write all these different equations on that and label them so that when a problem comes up on the exam, you just look at that card and be like, all right, which equation do I need? Sometimes that's the hardest part of figuring out these problems. The equation here is M1V1 equals M2V2. Okay, it sounds a whole lot like, Boyle's law. P1 times P1V1 equals P2V2, but it's M1V1. So M1 is the molar concentration. That's the molarity. V would be the volume. All right. So let's do a dilution problem then. Let's do it. And again, here, you're going to be given 3 of the 4 parts, and you're solving for, the part that you're missing. So here's our equation. If I have 75 milliliters of 3.5 molar glucose and you dilute it to 450 milliliters, what is the new concentration? Okay, it's a total great example about a dilution problem. So this one, just label the different pieces. This is V1 because units of milliliters means it's a volume. This is M1 because you have units of molarity. This has got to be V2 over here because it's units of volume. So we're looking for what? What are we looking for? The new concentration. M2. So let's first rearrange our equation. We got M1 V1 equals M2 V2. I want to solve for M2, so I just need to divide both sides by V2. Cancels out right here. All right, so M2 is going to be equal to M1 times V1 divided by V2. And you can keep it as long as your volume is in both either liters or both in milliliters. It doesn't matter as long as the units on the volume are both the same. You could work the problem with liters, you could work it with milliliters, but you can't work it with liters and milliliters. So we'll just plug everything in. So M1 is 3.5 molar, and that's times the 75, 75 milliliters. And we're going to divide that by the 450 milliliters. What do y'all get? So our new concentration is 0.58 units there are molarity. So that's M2. Okay. Questions on that problem? Fairly straightforward, I hope. Okay. Next problem, another example. I can buy 1 molar NaOH. What is NaOH? Anybody recognize that? All the way back from chapter 5, we talked about acid-base solutions or acid-base reactions. Sodium hydroxide, very, very, very strong base. We're gonna be talking about NaOH a whole lot in chapter 10. I can buy 1 molar NaOH. I need 750 milliliters of 0.32 molar NaOH. How do I prepare this? Okay, so essentially, what are we given? Let's label our problem. All right. Whichever one is more concentrated, we'll call this M1. This is the initial concentration. What you need, the working concentration, this is your new concentration, M2. That's what you want. And so if that's the associated volume with M2, that makes this V2. So what we're looking for here is how much of this concentration NaOH do we need to dilute it to the 750 mLs? Okay. So we're looking for V1. So let's just rearrange our equation. We know M1 V1 equals M2 V2. So we're looking for V1, so we're going to divide both sides by M1. Move it over, cross divide, cancels out over here. So V1 is going to be equal to, we're going to just now plug things in, 0.32 molar, that's M2, times V2, which is the 750 ml, and divided by 1. How nice, 1 molar. So what volume of that concentrated sodium hydroxide, the 1 molar sodium hydroxide, what volume do we need? Is it 240 or 250? I got two different numbers in the chat. 0.32 times 750. Double check. 240. Okay. So 240 milliliters. So to actually answer this question though, how do I prepare this? You would probably, I don't know if I would have this as like a short answer type of question. Molly says, wouldn't you need to convert milliliters to liters? Molly, not if you're keeping both volumes in milliliters. I know that molarity is moles per liter, okay, but because we have molarity on top and bottom, that cancels out. All right, so you, as long as you keep both volumes and you know it's, if you start with milliliters, you end with milliliters. You can work, I mean, check me, you can check it. Do 0.32 times 0.75, and then you should get 0.24, okay? You can work it either way as long as the volumes are either both in milliliters or both in liters because you have molarity on both. Does that make sense? You should get the same answer. Okay. But to actually answer this, we didn't answer the question. We just answered what's V1 so far. How do you prepare this? So you would tell me something like this. You take 240 milliliters of 1 molar NaOH and dilute it to 750 milliliters. Okay, you would end with an answer like that. In one sentence, you could say that, all right? Or you could find the difference in the volumes and say, okay, if I need, my final volume is 750 milliliters, how much solvent would I add? You would just subtract off, I initially already have 240 milliliters, okay? And so I have 240 milliliters of 1 molar, and so 750 minus 240 would be what? Is that 510 milliliters? You would add, you say, I take 240 milliliters of my 1 molar NaOH and add 510 milliliters of solvent to dilute it to my 750 milliliters, something like that. Okay, either answer would be okay. That's how much solvent you would add. All right, so those are two examples of dilution problems. There's going to be at least one dilution problem on the exam. It's a simple M1, V1, M2, V2. So I'm going to put a pin in dilutions. We're actually moving on to another topic now. We're covering lots of topics today. We've covered how to use molarity as a conversion factor, dilutions, and now we're going to talk about electrolytes, okay? We all know electrolytes are important. We've actually introduced this word way back in chapter 3, and you guys probably just from common language know what the word electrolytes are. These are ions dissolved in a solution. We call them electrolytes because the solution, do y'all know why we call them electrolytes? It can conduct electricity. Now, some solutions can't conduct electricity very well, but ions are charged, right? So if you have charged particles in a solution, it can conduct electricity, sometimes only very weakly. But anyways, once ionic compounds are dissolved, we talk about the ions and not the compound anymore, right? Especially, we know we do this with blood. We don't talk about sodium chloride in your blood. We talk about your sodium levels or your chloride levels, okay? So to illustrate this point to you, look at the picture of the beakers I have down here. If we add two totally different compounds into these beakers, sodium chloride and potassium bromide in the first beaker, and in the second beaker, two different compounds, sodium bromide and potassium chloride. Okay, those are two different compounds in each one. But in solution, what's going to happen? You're going to get Na plus, you'll get Cl minus, you'll get K plus, you'll get Br minus, and they'll all be just floating around mixing together. Okay, what's going to happen in the other beaker? Again, you'll get Na plus, you'll get some Br minus, you'll get some potassium, and you'll get some chloride ions. Now look, once it's all dissolved into ions, what do you notice about the two beakers? They're identical, okay? We don't say that we added sodium bromide. You wouldn't know if you were just looking at the solutions. You wouldn't know what compounds you added, okay? Because everything's in ion form. Now, so that's just a little bit of an intro on electrolytes. There are, however, though, as you can see, the tile on this next slide, there's strong electrolytes, there's very weak, and then there are substances that we call non-electrolytes. How do we know the difference? By the way, I still encourage you to read along in your textbook, the sections that are relevant to our lecture. So this is a figure out of section 9.8 of the text. A strong electrolyte, let's talk about those first. A strong electrolyte, we know that because it will completely ionize. What does that mean? Can I scroll to the slide above for 2 seconds? Is that good, Bailey? You bet. All right, back to strong electrolyte. So a strong electrolyte completely ionized. What does that mean? Something like sodium chloride. This is always going to dissolve. It's going to dissolve as fully as it possibly can unless we were to hit a solubility limit. So you're going to get all products, all right? And we indicate that with a single arrow, okay? I'm going to highlight that in like blue, okay? A single arrow. There's no reverse reaction here. It just goes all to products. So I'll just write that in. You are going to get all products. You will have no sodium chloride as a solid left over. It'll be all ions. That is a strong electrolyte. A weak electrolyte would be something like, here we have acetic acid, all right? CH3, CO2 with an H. Sometimes you see it as HC2H3O2. It's written different ways, but this is acetic acid. And it will not completely ionize. So it will, what we say, it will partially ionize. So some of the acetic acid will make your acetate an H+, okay, because it's an acid. Acids donate or they give away a hydrogen. But then you'll also still have some of your full acetic acid compound left in the solution. All right, so you could draw that with a reverse arrow. You'd have both reactions happening. Partially ionize. All right, what is a non-electrolyte? This does not form ions, okay? So it's something that's more like a biological molecule. So like glucose, fructose, sucrose, something like that. And as a solid, what are we going to talk? What does this look like? Maybe you have a big chunk of glucose, and it's all these individual glucose molecules, and they're bound together in a big, solid, arranged form. That's why you see solid right here. Okay, And on the product side, it's just dissolved into individual glucose molecules. And now they're fluid and they can move around, okay, past one another. All right, so they're no longer bound together in a solid. Now they're just individual glucose molecules. All right, that's kind of what that would look like. So no ions, right, on that one. All right, so I have a poll question. I want to know if you can identify on these next ones shown down below, which one is a strong electrolyte, which one is a weak electrolyte, and which one is not an electrolyte, based on what we just talked about. So the question says solution 1 is strong, weak, non-electrolyte, and you're going to identify that for solution 2, which would be the insulin, and solution 3, which is the HCl. Okay, we're only 70% voted. We got about 10 people left. So again, no math to do here, no problems to work out. You're just looking at, based on what we described, strong, weak, and non-electrolytes, which one of these down below? Look at the arrows. Is it a double arrow or a single arrow? Is it making ions or no? All right, I don't see the numbers going up anymore, so I'm going to end the poll. All right. Share results. So this is what you guys voted. Let's see, for the first one, we said weak electrolyte, okay? So H3PO4, this is phosphoric acid. And what we notice is that it does dissolve in water, okay, into ions. So we do get ions. Oh, I'm missing something here. I'm missing a minus charge. Okay, that should say, it should be black, minus. So we do get ions, but we got the double arrow, which indicates that we're also going to have some of our initial compounds. So this is definitely weak. That's a weak electrolyte. All right, solution 2, we've got insulin as a solid, making insulin in aqueous form. There's no ions here, so pretty much everybody said non-electrolyte, and that is correct. Okay, this is a non. Whoops. All right, no ions there. So that's a non-electrolyte, just like the glucose example. All right, then HCl. We got a single arrow, so most everybody picked strong electrolyte because we do not have a reversible arrow here. So you're not going to have any of your HCl when it's left. You're going to have all ions. All right, so this is a strong electrolyte. Okay, questions on that? All right, so again, this is totally an example of a style of a question I could give you on the exam. Here's 3 different reactions. Identify which one's the strong electrolyte, something like that, okay? All right, so that's electrolytes. So now we're moving on to another topic. We're covering a lot of topics today in chapter 9. And that is the topic of equivalence. Has anybody ever heard the term equivalence before? If so, what setting have you heard it in? Or how have you heard of it? Equivalence. We're going to abbreviate this EQ, but with a lowercase q. Okay, we abbreviate equilibrium as E capital Q. So this is E lowercase q. So I know it's the same letters here, but don't get that mixed up. E lowercase q is equivalence. E capital Q is equilibrium. Totally different thing. All right, so here we're going to talk about solutions from the standpoint of equivalence. All right, so we talk about molarity as a unit that we use to describe concentration of solutions. in moles per liter. But here, if we're talking about a solution in terms of equivalence, it would just be equivalents per liter. And what is an equivalent? Okay, it is an equivalent is the number of ions that carry 1 mole of charge. Okay, what the heck does that mean? 1 mole of charge. Well, we know ions carry charge, right? Every ion has an associated charge, all right? Calcium, what's the charge associated with calcium? +2. Aluminum, what's the charge associated with aluminum? +3. Okay, every ion has a charge. We know this, even negative ones. Fluorine, as an ion, carries a -1, right? So every ion is associated with a certain charge. So here we're just measuring the charge, not the concentration of the ion. We're measuring how much charge is present. So it's kind of, students sometimes have a tough time comprehending this. But why are equivalents important? All right, and specifically, sometimes you'll hear this term. I'm going to highlight this down here. Milli equivalents. This is more commonly what we'll talk about with equivalents of things in our blood. And I'm going to show you an example of how this is important. I brought a show and tell item today, but let me preface this with a story. Anybody have children? My daughter can get car sick sometimes. So, but anyway, she's just prone to throwing up. But one time she got the stomach bug. I don't know if anybody caught the stomach bug. It was really going around earlier this year in like February. But it hit our house end of January. And she got the stomach bug and she literally threw up from like 11 p.m. to 4 a.m. Bless her heart. She's 2 years old. So I was just like laying there with wide eyes watching her all night long because the 2-year-old doesn't know how to tell you when they're about to throw up. So this is my initiation into motherhood. I've never caught so much throw up on myself in my life. But anyways, the next day, I gave her some of this. Anybody recognize? So pediatric electrolyte. It's called Pedialyte. There's a brand for it. But I was looking on this box and look, can you see the units there? You guys read that? Is it kind of blurry? Yeah, it doesn't taste very good. Can y'all see the MEQ on the numbers there? Is it kind of blurry? All right, so it seems like when you take stuff like a Pedialyte, okay, it might be the reason you drink Gatorade. You're trying to replace, your body is deplenished out of electrolytes, okay, and that can be bad. When we're thinking about this is actually a huge problem in a lot of third world countries where they don't have like proper sewage or sanitation in place. And then you have diseases like cholera, which is widespread. One of the #1 deaths of children, and it's really sad, but is extensive diarrhea that can happen from diseases like cholera, okay? And when that happens, the body enters a state where you're extremely deplenished of electrolytes. So there's ways to treat this. One of the ways you can treat this is hydration. It's called hydration therapy. Anybody heard of that? When your body's deplenished of electrolytes, you can do hydration therapy to balance out your electrolytes again. All right, so this balances when the body is deplenished. Oops. Okay, I totally don't think I spelled that right. Deplenished, diplenished, deplenished. That doesn't look right. Deplenished, when your body is missing or low on electrolytes. You can do hydration therapy, all right? So you'll drink things like this. So this is why equivalents are important, because a lot of times electrolytes are measured in equivalents based on the charge levels that we need in our blood. So let's look at some examples. How do we begin to measure equivalents? Well, if I have 1 mole of sodium, every sodium ion has a plus charge. So if I have 1 mole of sodium ions, I have 1 mole of +1 charge. Does that make sense? I have a mole of charge, positive charge. Don't overthink it. It's really as simple as it sounds. You're just looking at the charge on the ion. So that means I have 1 EQ, 1 equivalent. That's 1 mole of charge, because that is what an equivalent is. It's the number of ions that carry 1 mole of charge. All right, if I have 1 mole of calcium, we know the associated charge is a +2. That means I have 2 moles of +1 charge. Okay, I'm just looking at how many, I need 1 mole of positive charge. So that's 1 mole of +1 charge. So if I have a +2 charge on my calcium, if I break it down into +1 charge, I got 2 moles of +2 charge. Or you could say I have, no, that's the best way I want to write it. So that's 2 equivalents, right? Double the charge. If I still have 1 mole of it, I have double the number of equivalents. What if I have half a mole of calcium? 0.5 mole. Then I should have 1 mole of, I have half the amount. Okay, I had 1 mole in the previous problem. Now I have half of that. So I should now have, instead of 2 moles, just 1 mole of +1 charge. And that should just be 1 equivalent, just like what we saw with the sodium. Okay, am I losing anybody right now? Makes sense so far? So the point we make after those 3 things is that 1 mole of sodium has the same quantity of charge as half a mole of calcium. All right, that's kind of what we gathered. Both of these are 1 equivalent. We're just looking at the charge here. Here's an actual table from chapter 9 showing you the concentrations in MEq, which is the milli equivalents of what we actually need in our blood for all these different. You can see sodium, it probably makes sense. Sodium and chloride, we need the most of those. You always need to maintain good sodium and chloride levels. And then you need smaller amounts of like calcium, potassium, magnesium, bicarb, and other things. Okay, so I'm going to work a couple more problems to make sure we comprehend what equivalents are. All right, so I want to ask you this question. How many equivalents of aluminum cations are obtained from 1 mole of aluminum plus 3 cations? How many equivalents is this? If I have 1 mole of Al plus 3 or 3 plus, how many equivalents is that? Kylie says 3. Okay, how do we determine that? Well, I could say I have, if I break it down into +1 charges, I've got +1, +1, and +1, right? And I just have 1 mole of these cations. So that means I've got 1, 2, 3 moles of +1 charge. So that would be 3 equivalents. And if I ask you how many milli equivalents, we know milli is 1/1000, or there's 1,000 milli in 1 equivalent. So that would be 3,000 milli equivalents. Okay, last problem, because this can be done with negative charge too. It doesn't differentiate negative or positive. It just says 1 mole of charge. So let's look at an anion. So how many equivalents of fluorine anions are obtained if we just have 1 mole of F minus 1? Again, don't be thrown off by the negative. It's just, we got 1 mole of -1 charge. So I've got 1 mole of -1 charge. So that equals 1 equivalent, okay? All right, hopefully that makes sense. I'm not gonna get any, I'm not gonna throw crazy complicated questions on here. Now, if I had a compound like NaCl, and I said, I give you 1 mole of sodium chloride, how many equivalents do I have of this? Okay, you would just break it up and say, I got 1 mole of Na plus and 1 mole of Cl minus. So I got 1 mole of positive and 1 mole of negative. That would be 2 equivalents, all right? So I could give you a compound, but again, you just break it apart into the ions. You look at what kind of charge it has and how many equivalents from each of the cations and anions, and you just add everything up in the end. Okay. I'm skipping over this next stuff. It's not essential. It's kind of an add-on if we have time. It is a cool property of solutions, but we're going to skip over these colligative properties, or what they call, of solutions, elevated boiling points, and anyways, let's go to the last big topic. So we got about 13 minutes left. Osmosis, okay? You guys know what osmosis is. You've talked about it in your biology class, haven't you? Hopefully. All right. So this should be a little bit familiar, which is kind of nice, but we're going to look at it from a chemistry standpoint. We're going to measure osmosis with chemistry units. Who's excited? All your faces just look like painful. All right. This is not osmosis, although this is what we're taught growing up, right? Anybody hear that story growing up? Like you just sleep on your textbook and through osmosis, all the knowledge will enter your brain. How many of you would actually sleep on your chemistry textbook if that's the way it worked? Raise your hands. I know you would. I know you would. I wish, right? Okay. But it's not exactly how osmosis works. So what is osmosis? It is the passage of, so this is the definition. Please know this definition for the exam, okay? Put a big old star by it. It is the passage of solvent, okay? This is a little antithetical to what we're used to thinking, okay? It doesn't, we're used to thinking about solute particles moving and measuring the solute concentration. Osmosis is focusing on the solvent, not the solute, all right? So I'm gonna highlight that because I want you to know it's solvent. Through a semi-permeable membrane. What does that mean? Semi-permeable membrane.
It's like selectively permeable, like only some things can move through.
Yeah, so usually small things can move through and not big things. Think of it like a filter. So what would have a semi-permeable membrane in the body?
Like cells.
Yeah,
Cell membrane.
cells. We all have all tissues, all kinds of tissues are made up of cells. All of our cells have semi-permeable membranes. So certain things can pass through, bigger things can pass through, but sometimes it takes like a channel, okay, to pump certain things through the membrane. All right, so osmosis depends on the concentration of particles, okay? So this is kind of, don't get thrown off by this word. It's talking about things like ions and small molecules. We're just not differentiating, okay? We don't care about the particle identity. We no longer care if it's sodium or chlorine or glucose or insulin or whatever. We just, how many particles are present, okay, in the blood or in the cell. We care about the concentration, how many, not which particle it is, right? Which is also kind of bizarre for us. We are usually measuring the identity of the particle or naming it as well. So what is osmolarity then? How do we measure this? It is just the number of moles of particles per liter of solution, all right? Moles of particles, that is an osmol. Moles of particles per liter of solution. All right. So I want to look at this next bullet point before I look at the picture. If you have 1 molar sodium chloride, I want you to tell me, so again, we're not naming the cation and the anion here. You're just going to simply tell me how many particles would you get, all right? How many moles of particles would you get? If you have 1 molar, so I'm going to zoom in for a second. I'll be right back out in a second. I would get 1 mole of Na plus particles, and I would get 1 mole of Cl minus particles. That makes sense? You're identifying how many things it's going to break up or dissolve into, and we're just calling those particles for the sake of osmolarity. So if it's per liter, which it is, this is 2 osmol. Okay. 1 and 1 make 2. Okay, what about glucose though? Glucose is different because glucose doesn't dissolve into ions. We actually already identified that with the strong, weak, non-electrolyte thing. So because of that, if I just have 1 molar glucose, I just have 1 osmol of particles, okay? Because it doesn't dissolve, it doesn't break down into any ions. All right, so here, if we're looking at these 2 pictures, if you were to count up all the red dots, which are indicating particles in this case, and compare this side has 3 times more, okay? So we'd say it's triple the osmolarity, 3 osmoles compared to 1 osmol. If this is per liter, if this was a liter of solution, okay? So if that's the case, what osmosis is going to do, don't look at the next slide. If you do, you're cheating. Which way, if we're trying to level this out, which way is osmosis going to work? Remember, it is the passage of solvent. So which way is the solvent going to flow? The way osmosis works is it tries to neutralize things that have different osmolarities. Okay, it tries to neutralize. Okay, so if this is a semi-permeable membrane right here, would the solution flow towards the right or would it flow towards the left? Okay, so there's a gradient. You've probably heard the word gradient in your biology classes before. And the way gradients work, solvent always moves from an area of low concentration towards an area of high concentration. I'm going to write that down. I wish I had more space on this slide. Okay, so when you have a gradient, I'm going to zoom in up here. Solvent flows from high concentration to low concentration. Wait, I wrote that backwards. I'm so sorry. I was not even thinking. It flows from low towards high. It flows from an area of low concentration to high. I wrote that totally backwards. All right, so if we've got low on the right side, high on the left side, the way this would flow is the solvent would move over here to try to lower the concentration of the high side. Does that make sense? That's the way osmosis works. It's kind of backwards of what we think. So you end up with solutions that look like this. Okay. Now they're equal osmolarity. Okay. So solutions that have equal osmolarity, we call these isotonic. Sounds like a drink. Isotonic. Same osmolarity, same number of particles per liter. Okay. So keeping with osmolarity or things that are isotonic, if we don't have equal osmolarity, okay, here we have equal osmolarity, 2 osmol, 2 osmol. But up here, we did not have equal osmolarity. We had 3 and 1. Okay, so what do we call it when you have a solution that's higher osmolarity? Okay, for example, the side with the 3 osmols, we would call this hypertonic. And if you have lower osmolarity, we call this hypo. So you got isotonic, hypertonic, hypotonic. Iso, hyper, and hypo. So I'm going to launch a poll question because these can be a little confusing as well. I want you to think about these words, iso, hypo, and hyper, and based on what we just talked about. Solution A has an osmolarity of 3 osmoles. Solution B has an osmolarity of 5 osmoles. So solution A is it iso, hypo, or hyper compared to solution B? You're describing solution A. Solution A has a lower osmolarity, 3 osmoles. Solution B has a higher osmolarity, 5 osmoles. So I want you to practice using these words. All right, we got 88% voted. I don't see the numbers going up anymore. In the poll, most everybody said hypo. Okay, whoever threw it isotonic, double check. Okay, if it's a lower osmolarity, we call that hypo, right? Higher osmolarity. So solution, if I was asking you what is solution B compared to solution A, can you go up to the hypertonic definition again? Molly, right here, is that what you're asking? If I was asking you what is solution B compared to solution A, then you say solution B is hypertonic because it has a higher osmolarity. But I was asking you to describe solution A. All right. So that's a little bit on osmolarity. Molly, did I get to where you wanted? Did you want to see this definition up here, the gradients? Okay. So we're going to do this slide, and then I really want to finish with this slide right here with the blood cells. I think we can do that in 4 minutes. So could totally ask a question like this on the exam too. When calculating osmolarity, ask yourself, how many particles, how many ions are often the word we use for particles here, will this compound produce when dissolved in solution? All right, so we're going to calculate the osmolarity. We're probably just going to do 2 of the 3 for time's sake. So I have 0.5 molar KCl. So how many different particles are we going to get out of potassium chloride? I will get, if I have 0.5 molar KCl, I will get 0.5 molarity. Molar is mole per liter, right? Of K plus I will get 0.5 mole per liter of Cl minus. And then you're just going to add that up. So I'll get 0.5 molar of this particle, the potassium particle. I'll get 0.5 molar of the chloride particle. So total, that would be 1 osmol. One osmol. All right. I want you to do calcium chloride. This one's a little more complicated. How many different particles would you get? I got 1 molar calcium chloride. I'm going to start writing it out as well because we're getting low on time. So I would get 1 mole per liter of Ca2+. We're not concerned with the charge here. That's equivalence. Okay, so ignore the charge. We're just looking at particles. Plus I would get, I've got 2. So you could write it out separately. 1 mole, you could do this twice per liter of Cl minus, minus, plus another one. We got 2. We'll get 2. Or you could write 2 mole of the Cl minus, all right? Because you're going to get double the chlorine. You get 1 calcium and 2 chlorides. So then you add that up. 1 plus 1 plus 1, that would be 3 osmoles. Does that make sense? How to calculate an osmolarity? Again, I think this is key up here. When calculating this, just identify how many different particles am I going to get from this compound. And then look at the concentration. Apply that to every particle. We carried the 1 molar into every particle. And then you just add them all up. That'd be 3 osmoles. Okay, in the remaining minute of class. If you need me to come back to this in just a second, I will, but I gotta address this slide. So here you have 3 different pictures of red blood cells. All right, this is red blood cells in an isotonic solution. You can see they look like a nice little donut the way they should. But look at the ones in the hypotonic solution. They're very swollen, okay? So when you have red blood cells in a hypotonic, I'm going to turn this to white really quick. Hypotonic solution, meaning the solution out here is a lower osmolarity, a lower concentration of particles, all right? So that means in the red blood cells, this is higher osmolarity. So what the solvent does, remember it's the solvent moving, and I know I'm at time, but it rushes into the red blood cell. And that's what causes them to swell up like this. Okay, remember it's solvent moving here, and it goes from a low concentration to high concentration. There's a gradient. Last thing, when you have red blood cells in hypertonic, okay, so what that means is that you have lower, backwards. You have higher osmolarity out here. So from the red blood cell, which has a lower osmolarity, all the solution is going to rush out into the surrounding areas, all the solution in the red blood cell, and then they're going to shrivel up, okay? Sickle cell anemia, you've probably heard of that before. If you're anemic, this can happen. It's a bad state for your red blood cells. But anyways, that's the last slide we're going to get to. Sadly, I wanted to talk about osmosis and oxygen transport and then dialysis for kidney patients, because osmosis is at play here with filtering your blood and then how oxygen moves out of our blood into our cells. But we don't have time, so these 2 things won't be on the exam.